Hi, I'm Tim Komar, and today we will talk about tangent lines, limits, and derivatives. We will illustrate how to calculate some standard limits, and these limits arise as derivatives or slopes of tangent lines. This video is appropriate for students in a first semester calculus class or students in EP calculus. So first, the derivative of a function f at x equals a is the following limit here, which is typically written here as f prime of a. And it's a limit of difference quotients written in two ways here. The limit as x approaches a of f of x minus f of a divided by x minus a, or equivalently, the limit as h goes to 0 of f of a plus h minus f of a over h over here, if the limit exists. So if the limit indeed exists, we say that the function f is differentiable at x equals a. On the geometric side, if f is differentiable at a, then the curve y equals f of x has a tangent line at the point a f of a with a slope of f prime of a. And an equation of this tangent line can be written in the point slope form as y equals f prime of a, the slope, times x minus a, the x coordinate of the point, plus f of a, the y coordinate of the point. So for our first example here, let's find an equation of the tangent line to the curve y equals 3x squared minus 5x plus 4 at x equals 1. So for our solution here, we're going to define f of x to be 3x squared minus 5x plus 4. And we're going to calculate the function value at 1 here by substituting 1 into the function expression, and we get a 2 out of that. So the point where the tangent line meets the curve is 1, 2. So the slope of the tangent line now, using one of our versions of that limit definition of the derivative shown on the first slide, is given right here. So f prime of 1 is the limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. We now calculate it. So first we've just rewritten it over here. And now on this next line over here, I've substituted the 1 plus h in for x into our function expression. And then I've also substituted 1 into our function expression over here. And now we're going to do a little bit of algebra so we can eventually calculate this limit over here. I'm going to expand the 1 plus h squared into the 1 plus 2h plus h squared. And I'm simply going to write out the three terms here still separately. For f of 1 is just 3 minus 5 minus 4. What we're going to see as we move on over here, leaving those terms separate right now, we're going to see how get some algebraic simplification over here, which can generalize to similar computations for other polynomials. So here now we're going to distribute that 3 through the first three terms over here, 3 plus 6h plus 3h squared, and then distribute that 5 minus 5h plus the 4, and then minus 3 plus 5 minus 4. So now here's the fun part. We see that these 3's cancel out. We see that the 5's cancel out, and we see that the 4's cancel out. So in other words, any term that did not have a factor of h canceled out over here. So our numerator over here is going to be 6 plus h plus 3h squared minus 5h. And yes, we have a common factor of h there. Now, we factor out that h in the numerator and cancel out these h's over here. So we're now left computing the limit as h goes to 0 of 6 plus 3h minus 5, which is just 1, and that is the slope of our tangent line. So our equation of our tangent line, again, given by f prime of 1 times x minus 1 plus f of 1, is simply going to be 1 times x minus 1 plus 2 over here. We see the curve given here in red, the tangent line at the point 1, 2 given in blue, and yes, this is just a simplified version of that equation of the tangent line here. Our next example is going to illustrate the limit calculation involving a square root. So here we have the curve y equals the square root of x, and we want to find the equation of the tangent line at x equals 4 here. So first, we're going to let f of x be the square root of x, our square root function. So f of 4 is just 2, and the point where the tangent line meets the curve is simply the point 4, 2. This time we're going to use our other version of the limit definition of the derivative here. So f prime of 4 is going to be the limit as x approaches 4 of f of x minus f of 4 divided by x minus 4. So now we're going to calculate this. So f of x again is a square root function. F of 4 is just 2. And now here's what we want to look at. If we try substituting 4 into the denominator, we get a 0 in the denominator. And that's pretty bad to begin with. But also if we put 4 in the numerator, we're going to get 0 in the numerator too. So we really end up with a 0 over 0 in determinant 4 here. So we're going to need to do something to be able to compute this limit over here. And at this stage of the game, we're going to take an algebraic approach for this. And the idea behind these ones involving square roots quite often involves the concept of difference of two squares, just from algebra over here. So what we're going to do is we're going to multiply the numerator and denominator by the square root of x plus 2 now. So in other words, it's the same thing that we had in our numerator, but now with a plus sign. And so that we actually have expressions that are equivalent, except when x is equal to 4 over here, we are going to multiply on top and bottom. So when we multiply the square root of x minus 2 times the square root of x plus 2, we just get, again, via difference of two squares, x minus 4. And the x minus 4's cancel out. So we're simply left with calculating the limit as x goes to 4 of 1 over the square root of x plus 2, which is just 1/4. And that is the slope of our tangent line. So now the equation of our tangent line can be written down, first generally here is f prime of 4 times x minus 4 plus f of 4. But here the slope was 1/4, and the point again is 4, 2. And yes, it has been simplified down in this version of the picture down here. We see the red square root curve, we see the blue tangent line at the point 4, 2. For our third example over here, we want to find an equation of the tangent line to the curve y equals 1 over x at x equals 5. So here we're going to let f of x be 1 over x, so f of 5 is just 1/5. And the point where the tangent line meets the curve is just the point 5 1/5. And we are going to use the first version of the limit definition of the derivative that we used in the first example over here again. So f prime of 5 is going to be the limit as h goes to 0 of f of 5 plus h minus f of 5 over h. So we're now going to first substitute in 5 plus h into the function. So we get 1 over 5 plus h. And then f of 5 we already had as 1/5. And now here is going to be our technique when we are dealing with these fractions over fractions and these limit calculations over here. In the numerator here, we have a least common denominator of 5 plus h, 5 times 5. So we are going to multiply both the numerator and denominator by that least common denominator of 5 times 5 plus h. When we multiply this by the 1 over 5 plus h, the 5 plus h's cancel out and we just get a 5. When we multiply it times the 1/5, the 5's cancel out and we just get a 5 plus h. And simplifying that, we simply get a minus h in the numerator. And I bet you can see where this is going from here. The h's cancel out, and we simply now have the limit as h goes to 0 of minus 1 over 5 times 5 plus h, which again is going to be negative 1/25, which is going to be the slope of our tangent line. So here again, the equation of the tangent line is going to be f prime of 5 times x minus 5 plus the function value f of 5, which in this case here, so y is going to be negative 1 over 25 times x minus 5 plus 1 over 5. And we see the 1 over x function right here in red, the tangent line in blue, and the point of tangency at 5/1/5. And yes, the form of the tangent line here has been simplified a little bit. One last thing before we conclude, I just want to go over another example that involves the rational type expressions we saw in the last example. So quickly to remind you what the derivative function is, the derivative f prime of a function f is defined as this particular limit of a difference quotient over here. So it looks like what we had before. So rather than having a number a in here, this is for any x for which this limit is actually defined over here. So again, it's the limit as h goes to 0 of f of x plus h minus f of x over h. And again, this only works when the limit exists. So now we're going to compute the derivative f prime of the function defined by 1 over x plus 2. So first thing we're going to do is we're going to plug in x plus h into the function, so we get 1 over x plus h plus 2. And we're going to plug in x into the function, we're going to get 1 over x plus 2. And now we're going to follow the same thing we did in the last example, just to emphasize this again. Our least common denominator from the numerator here is going to be x plus h plus 2 times x plus 2. So we're going to multiply that by the numerator and by the denominator over here. And when we multiply the x plus h plus 2 times the first term, times x plus 2 times the first term over here, the x plus h plus 2's are going to cancel out, and we're just going to get the x plus 2. And then when we multiply the x plus h plus 2 times the x plus 2 times the 1 over x plus 2, the x plus 2's cancel out, and we just get the x plus h plus 2 over here. And that simplifies nicely to a minus h again. So h's cancel out, and we have a limit that we can compute. And we end up with the function minus 1 over x plus 2 quantity squared. And that is the derivative of our function here. So again, I'm Tim Komar. I am a math tutor. I am available for math tutoring. There's my email address. There's the website for my tutoring website. And I can tutor anything in high school and college mathematics for you. So look forward to hearing from you. Thank you.